So this is the last presentation in this conference. So my title is Large-Scale Silicon Quantum Computer, and there are principal investigators, PIs. So myself, and Nagata Sensei from Kobe University, Kodera Sensei from Tokyo Institute of Technology, and Nakajima Sensei from Riken, and Yoneda Sensei from Tokyo Institute of Technology. So this slide shows the background and motivations. So scaling is one of the advantages of silicon qubits, but in fact they have only achieved up to 6 qubits. This picture had already shown in the previous presentation. So last year, a Riken group achieved 3 qubit operation with a quantum error correction. And also 6 qubit operation has been achieved from QTech group. So large-scale integration is still a challenge in silicon qubit quantum computers. This is a special issue of Nature on silicon qubit quantum computers. According to the opening article, they say the next milestone is to build a larger array of quantum dots. The goal of our project is to achieve exactly this milestone. Okay. So the question is whether the current silicon qubits are taking full advantage of silicon semiconductor technology. It has 2 major aspects. One is miniaturization here, and the other is the integration of large number of qubits. Miniaturization optimizes qubit structure, the size of the qubit, and the distance between qubits. And also it increases noise such as crosstalk. On the other hand, integrations brings many advantages. It obtains a large number of qubits with remarkable uniformity. And it also handles a large number of wires from qubit arrays by integrating CMOS circuitry. And also it achieves high precision control of qubit array. We expect a lot about these features. And of course, there is a drawback. So integration results in high heat density. Anyway, we need to take advantage of both of these 2 aspects. So this slide shows our approach. The x-axis shows the quality or fidelity, and y-axis shows the quantity or number of qubits. In conventional, we call bottom-up approach. We focusing on quality and starting with a single qubit operation and increasing the number step by step. In contrast, we take a top-down approach in which firstly we integrate a large number of qubits and then improve the quality of these qubits with various technologies. So the final goal is to implement almost all the elements in a single fridge, as shown here. So nowadays, there are many experimental equipment outside the refrigerator, but we want to integrate almost all the equipment into the single fridge. This is a system we are developing. There are mainly 2 chips we are fabricating. One is qubit array chip. It contains a qubit array with a CMOS control circuit on the same die. It is implemented in the lowest temperature region of the refrigerator. And another one is a cryogenic control chip. It controls a qubit array, and it contains many control circuitry, including RF or microwave generator and many DC bias generation. It is placed at the 4K stage in the refrigerators. This system can be divided into 4 R&D teams, so they are the PIs. Today, we are introducing the progress of each R&D themes. First, let me introduce our qubit array chip. This is a schematic diagram of the qubit array. It contains 16 by 8 qubits, so totally 128 qubits. And it also, we have initialization qubits and a readout. In the following slide, we are introducing more detail step by step. First, I'm going to talk about the formation of qubit dot array, quantum dot array. It integrates CMOS circuit on the same die. And then initialization. We set a single electron in each quantum dot in the array, and then operation, and finally a readout. This is the formation of quantum dot array and the integration of CMOS circuitry. We have developed embedded qubit CMOS process. We call it QCMOS, which integrates qubit array here. It contains 128 qubits. The cross-section of the device is shown here. And the peripheral circuit, CMOS circuit, and the cross-section here around the qubit array. And this is the normal CMOS circuitry, so PMOS transistors and NMOS transistors. The same NMOS transistor forms the quantum dot with self-aligned MOS transistors between these NMOS transistors. So the distance between the quantum dots is around 100 nanometers. So even though we use a very mature CMOS technology, 100 nanometers quantum dot pitch can be achieved. We have also developed active silicon interposer that can integrate circuit on the active interposers. The feature is that heterogeneous integration is possible. So for example, silicon germanium qubit array and also a CMOS circuitry on the active interposers. We are developed on both in parallel. So this slide shows the initialization of qubit array. So this is the top view of the layout pattern. So I'm sorry, this figure is a little bit Japanese, but this is the quantum dot, 1, 2, 3, and here is a sensor, and this is a magnified picture. This is a cross section. So we developed a single electron pumping technique for highly reliable initialization. We have developed we have demonstrated 100 megahertz single electron pump transport with 1 hour stability and 99% accuracy at a temperature of 4K. Even though the temperature is relatively high, 4K, but the high accuracy was obtained. This is the platon. We can observe the clear platon as shown here. And let me introduce 2 qubit operations in progress. One is from Riken's group. This is the first demonstration of high-fidelity 2-bit gate operation that is above the error tolerance threshold. So this figures around 99.5 fidelity has been obtained. And this one is also from Riken group. It demonstrating the fidelity for achieving error tolerance with a silicon qubit array. It generated 3 qubit quantum entangled states. I'm sorry, this is also written in Japanese. I just noticed. So Anshira bit, data bit, and Anshira bit also, and encoded, decoded, phase error, and correction. And this figure shows the experimental results. The x-axis shows the phase error angle, and the y-axis shows the fidelity. So I think this is the world first demonstration of silicon phase error correction circuit. Anyway, remarkable progress has been made in small systems using silicon germanium qubit. The problem is it has been a challenge, still a challenge in qubit array using silicon MOS type qubit. So this is a comparison between Riken's group's silicon germanium qubit, and this is a silicon MOS type qubit in this project. So there are many complicated physical problems, so we are now theoretical studies and multiple device program are being proceeded in parallel. For example, silicon oxide interface roughness is a kind of a concern, I think, and also there is we use a shallow trench isolation to isolate the two devices. So it also causes fixed charges or defects due to the shallow trench isolation. In addition to the operation of qubits in small systems, another concern is the operation of qubit in qubit array system. So we use shuttling qubit operations. It separates the electron from the quantum dot, meaning that the qubit can move or shuttle. So this figure shows the detail of the array structure. So qubit array, 128 qubit, is divided into 3 regions. One is bus, aisle, and seat. And the qubit in seat can operate. So this is to dramatically rearrange the qubit without congestion. It suppresses crosstalk and enables all-to-all connections among up to 56 qubits in case of 16 by 8 qubit array, in this case. I think shuttling qubit creates a new category of qubit. So that is, for example, superconducting qubit is a static qubit, and conventional silicon qubit is also a static qubit. And the photon is a moving or flying qubit, right? So dynamical qubit is these things, and the shuttling qubit is categorized in this dynamic qubit. So it takes advantage of silicon semiconductor technology and use quantum dot quite luxury, as shown here. This is a demonstration of 6 qubit QAOA operations. In conventional, 6 qubits are used, and blue color means qubit operation is performed. So in contrast to shuttling qubit operation, so we can use more quantum dot, and some quantum dot are used for qubit. So we can move a qubit and operate to keep the distance between 2 qubits. So this is the readout. So readout is also a challenging operation sequence. So high fidelity, high frequency reflectometry remeasurement is widely used, as you know. A challenge is that it is difficult to support large-scale integration. So we have developed a PMOS sensor that is capable of detecting a single electron. This is a top view again. So there is a quantum dot, and we have a charge sensor, PMOS charge sensor here. This is the cross section of the PMOS sensor. So potential barrier here in the channel region of the PMOS is lower due to the electron confinement to the PMOS well. So this causes the current change on the order of nanoamps. This is the measurement results. If the difference in the number of electrons can be converted in the current change, and also the order of nanoamps. The sense amplifier circuit used in static random access memory or DRAM becomes possible. So we can integrate more readout circuitry on the same chip with quantum qubit array. So next topic is cryogenic control chip. We are developing a 40 nanometer CMOS control chip, and it's evaluating now. This chip is placed here, so 4K region of the refrigerator, and this is the photomicrograph, about 4.5 nanometers squared. And this picture is the implementation of 4K stage of diffusion refrigerator, and this is the measurement result. And it contains a timing generator. It can generate a sequence of the operation. Timing range is 1 nanosecond to 2 milliseconds, and the resolution is 1 nanosecond. And it contains RF microwave generator, 20 gigahertz microwave, including a PLL and mixer. So it means clock signal is the only signal we need to operate this chip. So we have arbitrary waveform shape mechanism, and pulse width is as shown here, and amplitude, the power is like this, and the phase error is like this. This is about 99% control fidelity, so it's not enough, I think. So we are developing second version of the control chip. Now this was fabricated, and now it is evaluating. And also we need a lot of bias control to control the qubit array. So we contain the 59 channels bias generators. There are some key circuitry in the control chip. So let me introduce two of them. So one is the cryogenic DA converter that is used to bias voltage generation. The resolution is 16-bit, and the feature of this DA converter is the size. This is very small. It's about 0.02 square millimeters per channel. So we can, so let's go back to this. We can place side by side at the pad pitch. So it contains 59 DA converters. And cryogenic temperature environment enable high performance analog circuitry. So we enjoy the circuit design at the 4K temperature region. And the linearity compensation circuitry is also implemented. So before calibration, so INL, so integral non-linearity of the DA converter is like this, but after calibration, it decreases to within plus minus 1 LSB. So the figure on the right shows the AD converter that is used to internal circuit compensation. The resolution is 11-bit and the speed 100 millisample per second. It also contains an offset compensation circuitry, but And this is the block diagram of control circuitry. So we have this AD converter here. So this DA converter is this one. So we have 59. And this is microwave generator. It needs some calibration. So we use this AD converters to calibrate this microwave generator. So hardware does not work well without software. So we are developing quantum operating system. So these are the results of this operating system. It contains a model that is digital twin, that is a copy of quantum array and their operating environment. It provides a feedback, so we can make a system containing a feedback control. And it also provides a multi-role use environment for various users. So there are many different types of users in quantum computers. So quantum physicists and quantum algorithm researchers and also engineers. So we have to support multiple users. So we make such kind of environment. So this is a key circuitry to monitor the environment in the 100 millikelvin regions. It is quite difficult to monitor this kind of regions environment. So we are developing extremely low power AD converters. It is less than 1 microwatt. So it can control the signal of qubit array that affect the fidelity of qubit. It is also implemented on the silicon active interposer. So qubit array is placed here. It is near from the this circuitry. Okay, let me introduce two more fundamental research progress. So one is hot silicon qubit. This is progress from Tokyo Tech. So high temperature operation of the qubit simplifies the overall system design. So this is very important. So we are taking this research, and we have observed weak temperature dependence of the charge noise in our silicon devices for both silicons and holes, as shown here. I think it shows promise for hot silicon qubit. And also, this is also the very fundamental research, but very important, error correlation. This is the progress from Riken and the Tokyo Tech Group. And we observed the world firstly the correlation of qubit phase noise between two qubits. So spatial correlation of qubit error becomes apparent when qubit arrays, which is related to ease of error correction. So we have observed relatively large correlation above 70%. So I think it shows the effectiveness of shuttling qubit operation. It means shuttling qubit keep the large distance between qubit, so it can decrease the effect of this kind of correlation of the charge noise. So in summary, quantum computer R&D is shifted from scientific curiosity phase to a technology development phase. So I believe for a quantum computer to have industrial value, it must be a large, in addition to be high quality. In this project, we are going to achieve a large-scale silicon quantum computer through a top-down approach in order to take a full advantage of silicon semiconductor technologies. In the past 2.5 years exactly, we have developed several key elementary technologies in addition to many remarkable fundamental research results. We will continue to demonstrate some qubit operation in small systems, and also we will move forward with system integration to achieve stable qubit operation and further improve the fidelity of qubit operations. Thank you.